First, thanks organizers and the staff for setting all this up. And thank you, all the audience, for coming here. And all together, let's witness the moment when computer vision embraces Kubernetes. Or let's say Kubernetes embraces computer vision because which is much older. But whatever, doesn't matter. My name is Yisui, a software engineer from Google. Today, I'm thrilled to share what I've learned by running a vision processing pipeline on Kubernetes. And given this session is a tech sharing session based on the facts from my hobby project during my spare time, please don't take anything as official from Google. And I'm not an expert of computer vision, so please ask simple questions. And this session will be mostly focused on Kubernetes. And given the content of this session will be a little dense, so I appreciate if you can hold on your questions until the Q&A session. Thanks. Now, let me introduce the project. This is my hobby project. So I built a robot which has a single camera. It can move horizontally like this, and it can also move vertically like this. It got two motors to move the robot around. And obviously, it also has two arms, a left one and the right one, of course, for just being cute or silly. And with a 4-node tiny cluster, it's an ARM-based cluster running a Kubernetes. So what I want to do is basically try to offload the compute-intensive vision processing and controlling tasks to the cluster. Because running these tasks is so power-consuming on the robot. And some people may ask me, why you are using a Kubernetes for controlling a single robot? Will that be too overkilling? Because using a simple mini PC or even a smaller single-board computer will be sufficient for that. Probably yes, but I have a few good reasons for using Kubernetes. The first is Kubernetes simplifies operations a lot. I know how I build the code, and I know how to pack all the binaries into containers. That's all, and leave all the rest to Kubernetes to perform all the heavy lifting for deployment and very easy upgrade and also downgrade. And the second reason for Kubernetes is it brings up this native support for scalabilities. Today, I have one robot to control, and probably I will plan to build more, for example, as kids' toys. And when there's more robots, definitely the workload will increase heavily. As long as I have enough hardware resource, the Kubernetes take care of them seamlessly. And the third reason about the ecosystem is actually the community. I'm in awe of the power of the community for endless creativity, and we can leverage so much tools and to focus ourselves on our business. And running a vision process on Kubernetes is definitely a non-common use of Kubernetes. And I think it's very interesting to have a try. So let's take a look at this vision pipeline. Actually, this can be built using Kubeflow. I haven't tried. If you are interested, there's a few Kubeflow related sessions these days, so you can attend. So in this pipeline, the robot will continuously take VJ-sized image in JPEG and send over Wi-Fi into the pipeline. When the pipeline receives the image, it performs some pre-processing tasks like decoding the image, formatting, converting the image pixel format, and do some resizing and cropping kind of stuff. Then it's sent to multiple data processing passes in parallel. So one of the passes is going through a SSD mobilenet neural network, which detects multiple objects from a single image. And the second pass goes through a OpenCV face detection And it detects rectangle regions of your faces from image, and then send these sub-regions into a face net, which extracts the features from this area of your face. And if you can map the set of features to a label, basically the robot has the capability to tell your name when it sees your face. The output of these data passes are actually small JSON objects, so we can easily share that with something like MQTT, which is a message bus, and to be consumed by controlling logic from there. And when running this pipeline on Kubernetes, we do meet some challenges. The first difficult problem is all about real-time processing, which requires a decision to be made within like 30 milliseconds. And it's heavily impacted by some facts like unreliable Wi-Fi network, and also the long-running compute-intensive tasks. And because of the tiny cluster, I don't have enough computing power on this cluster to support neural networks. So I have to use external neural network accelerators like Mobilenet, computer stick. And we need some additional work to make that work on Kubernetes. And also, the third one is actually an interesting one. When we're running Kubernetes on ARM with a Big.little architecture processor, I will talk about that later. So first, let's start with a simple problem to support the accelerators on Kubernetes. So first, let's take a look about the hardware spec. We got a robot. I don't want to duplicate that again. So basically, you can think that the robot has Orange Pi. You can think that as a Raspberry Pi 3 equivalent running Linux with Bluetooth and Wi-Fi. The cluster is running on a 4-node system, each equivalent with Samsung Exynos 5422 CPU. It's octa-core CPU. You think it's 8 cores, but wait, it's actually different. It has 4 big cores running at 2 gigahertz, and another 4 little cores running on 1.4 gigahertz. That's called Big.little architecture. And we also need corresponding Mobilenet computer stick for each of the nodes. And we will also run a Kubernetes 1.9 at a time when I experiment this project. So this is a picture of the cluster and the picture of the Mobilenet memory stick, neural stick, and when they are wired together. Okay, the first problem is how we want to use these sticks in Kubernetes. It's different from the common practice we are using a normal GPU. The stickers are controlled directly using the SDK from the application. And the SDK is using the libUSB to initialize the device. The initialize processor will first always offloading the firmware and then reset the device. As a result, every time the stick connects, the SD connects to the stick will recreate a new device on the host. So it's impossible to bind mount the device node into the container. Fortunately, the official document provides a simple Docker run command to run the SDK inside a container. So basically, we need a privileged container and run in the host network namespace. And we have to bind mount the host DEV folder into the container. Now we can start offloading the models. Offloading model takes quite long, depending on the size of your models. So it's infeasible to switching the model by offloading a new model into the stick during the runtime. The solution can be very simple by preload a few models onto the stick. And we can selectively run one model at a time. And if we have many models, we definitely need to distribute these models across multiple sticks as they are attached to different nodes. Then the pipeline becomes distributed. And we also want to build a service around these stickers to hide all the complexities for accessing these devices. Well, I was thinking about how we want to build these services. So one big concern is all about the input data. The input data is actually big. And especially for this stick, it had to convert every pixel channel into a half precision flow point. So basically, one pixel would take like 6 bytes. So usually, for VGA size image, it would take a few megabytes. If we think just through all these into a network, that will be a very heavy traffic. And can we think a different way how we build a service which doesn't serve through a network? What about using shared memory if all the ports can be co-located on the same node? Well, thinking about the TempFS and also mmap system call, I think we find a solution. And let me just explain the TempFS and mmap in case anybody here doesn't understand that quite well. So a TempFS is a file system on Linux which is complete in memory. So a file content saved on this file system basically sits in a physical memory page. And the mmap system call can map content of a file into a memory space or process. And the process can purely use the memory access instructions to access content of the file. So thinking about if we run mmap on top of a temp file system, that means we are directly mapping the physical memory page into the process space without copying any data. And thinking about multiple ports are using mmap on the same shared TempFS. So basically, they can share the same large amount of data without copying any of them. So that's the way we want to build this shared memory mechanism. And this diagram shows a more detailed mechanism. So on the left top side, this is DEV SHM. Normally, this is a TempFS mount point on most of the Linux system. This is on the whole system. And we create a subfolder on that. And in the auxiliary service in port in blue, and also in the app1 port in green, we bind mount this subfolder into these containers. So effectively, these two ports are sharing the same TempFS. When the app1 port receives the frame after pre-processing, it saves the image data into the TempFS using mmap. And it notifies the auxiliary service using whatever mechanisms. Because they are sharing the same file system, so the auxiliary service is able to see the file on the local file system. And it uses the same mmap system call to map the file into its own memory space. So after that, we can see the yellow block, the tensor image, is actually a single copy in the physical memory, but shared by two ports. So they are sharing the same data without copying any data. And the auxiliary service can offload the image data to the accelerator. And with the similar mechanism, they can also send back the result. OK, so after talking about this simple problem, we are come to the next difficult problem. It's all about real-time processing. First, let's take a look at some benchmark. It's all about the cost running some tasks. The first blue bar is a baseline of 30 frames per second rate from camera. And we can obviously find out the neural network computation takes significantly longer. As we remember, the real-time processing has the requirement of the decision to be made within 30 million seconds. But with this data, it seems mission impossible. But no worry, Tom Cruise has accomplished the impossible missions for at least 6 times. If I remember correctly, there's like 6 Mission Impossible movies up to 2018. Well, we needed some small tricks to accomplish this impossible mission. Please note that this highlighted word, effective. What does that mean? Effective actually makes the result looks like real time. So actually the decision is, looks like it's very responsive, but actually the decision can be made based on something more than 30 milliseconds ago, for example, even 100 milliseconds. Let me show you an example to demonstrate this idea. Let's assume even worst case. The object detection task takes a second to run. It's too terrible in real world, but just for example. And this task detects a Lego figure as a person. That's awesome. And it also detects this Lego car as a car, of course. And when it finishes, actually, we already received another 30 frames based on the 30 FPS rate. And what we do is basically we only take the latest frame and compare the content in the detected area with the frame a second ago. And we can find out the person area has no change. So actually, the result is still effective applied to the latest frame. While regarding the car, well, actually, that's a Lightning McQueen. He turns the face to us. And that area changes significantly. So this detection is no longer effective. And we just simply discard it. This mechanism is very useful when the robot is put in an environment when the surroundings are relatively stable in a short period of time. And with another example is basically the face detection and face recognition. It is a little different. The use case allows a little more delay. Just imagine the robot stares at you for a while and then calls out your name. Isn't that cute? So, okay, so at one end, we are trying to make the result looks like very quick. Now I'm working on the other end to make things work really fast by trying to parallelize the data passes. So from the pipeline, we can obviously find out there are two sequential groups of data paths that can be run in parallel. And to run these things in parallel, we have already discussed the memory shared mechanisms to collocate all the pods to effectively share large data when they generate during the execution. So from the diagram, we can easily see the face detection and recognition flow is running on a separate node from the object detection paths. And there's a few mechanisms to do that. We can label the nodes with models or even other mechanisms to collocate all these pods together. And there's another trick to push even further about the parallelism by duplicate the small input image to all the nodes. So when a robot sends the image to an endpoint, which is basically a service, which load balances to one of the receiving pods, based on the input image is small, the receiving pods will duplicate the image to other receiving pods across all the nodes. And all the nodes will also run the same pre-processing tasks as they are lightweighted, and they are running across all nodes in parallel, so there's no overhead. As a result, we have the same exact input data across all these nodes. So based on that, map reduce across nodes become possible and easier. And the tasks on each of the nodes just run over a slice of the image, and we can aggregate all the results in the reduced phase. And there are a bunch of coordination mechanisms we can use. For example, if we run the tasks using a static set, you can leverage the assigned unique sequence for partitioning and reduce. And not using that, you can use lead electric mechanism from Kubernetes, or you can build it yourself. There's another factor that impacts the real-time performance. I mentioned a few times, but not in details all about the Wi-Fi. Especially the 2.4 gig Wi-Fi with as many devices connected or with a heavy load from a device to router. Most of home routers cannot afford a consistent and reliable transport. And we use a simple mechanism by just processing the latest frame and ignoring all the dropped or delayed frames. Based on that, TCP is no longer a best protocol for that because TCP tried to deliver a guaranteed delivery, while UDP is good for that. It's send and forget. So regarding the compression algorithm, the H.264 is way better than the JPEG regarding the bandwidth. However, this protocol requires reliable connection like TCP and has lower loss tolerance. While JPEG has no dependency between frames, so we can easily drop frames. It works better on UDP. Okay, so we've talked about the simple problem and difficult problem. Now we come to the interesting problem. It's very special on ARM processor with Big.little architecture. So thinking about the case when we are scheduling a CPU-intensive task on a little core which runs slower, so this task will finish takes much longer to run. And if we run a accelerate offload task on a bigger core, does it run faster? No, of course not, because it has to wait until the accelerator completes. So this is a suboptimal situation in a Big.little architecture platform. So ideally, we want to schedule all the CPU-intensive tasks on bigger cores. Today, the Kubernetes scheduler doesn't support that on this level. The good thing is it opens all the cores to the container, so we can do that inside the container. But I'm not sure if we set the core affinity inside the container will impact the overall scheduling performance because the CPU consumption is actually different from what the Kubernetes schedule assumes. But anyway, if there's enough resources, not a problem. All right, I've covered all the things I want to share with you. I'd like to quickly revisit and before we can wrap up for the questions. So first, we want to support the Mobilenet computer stick on Kubernetes, so we can use a privileged container with host network namespace. And we want effectively share memory mechanism for share data across pods, which requires all the pods to be co-located on the same nodes with affinity rules according to data locality. And we use the simple replication mechanism to replicate small input images and also lightweight pre-processing tasks to further push the parallelisms. And the core affinity is important for performance on a heterogeneous architecture. So thank you. That's all I have, and thank you for holding up the questions. Now it's time to bring them up. Yes, please. Thank you.
So first wanted to say this is incredible work.
Thank you.
It's quite amazing. I had one question for you, which is, how do you think about designing a load balancer to run on ARM that and report the status of the accelerator, basically, and know like when you need to allocate a new? Oh, let me go again. Hello. So first off, this was an absolutely incredible talk. Quite some amazing work that you've been able to do in getting this system to work. My question was around load balancer, particularly in context of that Prometheus neural compute stick. How do you think about deciding what pod should be running the compute task, and how do you know like when the accelerator is active or how long the task is going to run for, things like that?
Yes, that's a really great question. Actually, it's very complicated. Today, I even didn't do that. I did all the things manually, by manually label all these stuff to make sure they are running on the same node. I have a few thoughts, maybe imperfect, but because we have service manage all the accelerators. So service knows what model they're currently running. And today, we can only run one model at a time on the stick. So basically, the service can report what's currently running on this node and which other available model can be run on this node. So based on that, some scheduling logic can be aware of the next task to be scheduled and which model it's going to consume. It can find out a available node which has this model able to run. But on the other hand, we also mentioned it's important to share data across all the tasks within the same data flow. And the schedule will also have to take that into consideration. Otherwise, you have to copy over the data. But if the task doesn't consume the intermediate data, maybe it doesn't matter because of the replication, we already have the input data across all nodes. So you are free to schedule. But there's definitely a lot of detail need to be figured out. I think that's a very great question for good research in future. Yes, please.
Yeah, I was wondering about your sharing the temp FS across multiple pods. Why not run the containers as part of one pod and just shared memory? Was there a compelling reason to have them split into multiple pods?
Thank you for the question. The question is, why not we just run all the tasks in one pod but in different containers? Why just separate them as different pods? That's a great question. I actually started by running all the tasks actually in one container. Or at the beginning, I just run everything in one process, so I don't have the problem. But later on, when I find out if I want to modify the vision pipeline, I'm adding more and more tasks into this graph. And I'm basically adding more code into this sort tree. For a small project, yes, that's much simpler to build everything into one binary. But I'm thinking about if we want to make it more easy to plug, and we don't want to interrupt a running pipeline by just adding a new path into the system, it will be much easier, especially with Kubernetes, by dropping a new pod into the system. And Kubernetes can basically effectively schedule the pod on whatever node. And that's the reason I came out this idea by trying to share the memory across pods. And I found it actually is workable and work the same way as sharing the same memory across the container inside the pod. So given that flexibility, I did a try on this path, and turns out to be reasonable.
One of the common things with shared memory is dealing with the coordination of them, because there's no, one issue that happens with shared memory is like knowing when the consumer should take from the shared memory and when that thing has been consumed. How did you deal with like coordinating that? Did you use like message queues and?
Yeah, this is a great question. I have tried a few mechanisms. Actually, there's a lot of ways to do. So first, let's go back to the example I just put in the slides. The application will create the file with, for example, UID. And it notifies the service about the file name because they are sharing the same file system. And the service will take that file according to the UID. And this notification mechanism can be through anything like even through a message queue, whatever. And in my implementation, I am also using the same mechanism using the shared file system to notify the service because the service has the capability to watch the file system. And if any change happens, it will be aware of which file changed, and it can basically read the file.
You said that Kubernetes doesn't support CPU affinity, so you're doing it inside the pods. How are you making sure that different pods have affinity to different CPUs?
We can't make sure. So it's basically all inside the pod. So what Kubernetes scheduler works is basically you can specify the amount of CPU you want to consume. Probably you can specify a number of cores. But I never specify a number of cores the CPU want to occupy, but just in general specify like megahertz of kind of things of CPU usage. So basically that opens all CPU to the container. And very likely, if you schedule multiple pods on the same node, they will share the same CPU. But as long as I want have the core affinity inside the container, it's okay for the Linux scheduler to coordinate between the processes sharing the same core. This is definitely not a perfect solution. But as I said, today I have enough resources, not a problem for me. But if there's restricted resources, that definitely a problem needs to be solved. Does that answer your question? Thank you.
We have another one over here.
Did you do anything to have Kubernetes schedule the neural compute sticks, or did you just have the nodes, the containers mounted directly to them?
Sorry, can you repeat the question?
Did you do anything to have Kubernetes schedule the pods to the nodes with the compute sticks, or just mount them directly?
You are asking, I'm doing anything about scheduling to schedule a pod to a node? Is that a question?
Specific to the accelerator.
Oh, specific to accelerator. So as I attach the accelerators to each of the nodes, so actually I'm running the accelerator service as like a daemon set, which is, can be a privileged container. And I will label the node according to the models loaded on the accelerators, and also define the label myself. And to particularly specify pod to be scheduled on the node, I will also put affinity rule on the pod. That's done all manually, very, very, very early and rough stage. So that's how it works. Oh, okay. Sorry.
Sorry about that. It's on. Have you thought about making your nodes, the Big.little nodes, actually seem like two nodes to Kubernetes, so you can then, Kubernetes would know to schedule them, and then you can label, I need big cores or I need little cores on your pods. And then Kubernetes scheduler could manage that. So it looks like you have twice as many nodes.
Yeah, so you are talking about I can split a node effectively into two virtual nodes, which only contains big cores and which contains little cores. That's a great idea. Depending on the complexity of the kubelet, it doesn't work quite well. If two kubelets running on the same host and try to let it split on some resource, that's very difficult based on the current implementation of kubelet. There are a lot of details I cannot tell because I don't know. Perhaps we can talk to some people working on the node kubelet, but today it's difficult.
So you talked about using different accelerators. I understand that. Can you clarify ARM? Like, how does that help machine learning workloads? So you had a slide that was talking also about ARM. Does ARM processors did I understand that correctly? ARM processors, or is it some kind of accelerator?
Oh, you are talking about the accelerator?
Yeah.
Accelerator is it's a offline computing device connected through the USB. Basically, it has its own CPU and neural network acceleration process built into this small stick. And it talks to your CPU using USB link. So how it runs, what's the architecture, I don't know. What I use it only through the SDK they provided. So you can think that as a remote computer and talk to them with a channel through USB.
Basically, you can also have, like, if it was a data center, you'd have like a GPU that would also be a use case, or something like some of the vendors are doing, like Google TPUs. So the same thing applies. These are accelerators designed for machine learning algorithms that can run faster and parallelize more.
Yes. So if the services can be abstract in that way, it can support different kinds of accelerator, including GPU and TPU, all kind of stuff. But GPU and TPU are working in a different communication model, which may be more effective than being wrapped over this service. So that part I don't know. So maybe worth to figure out.
Thank you for the talk. Very exciting and challenging task to accomplish.
Thank you.
From your applications perspective, what kind of features do you expect from Kubernetes, but it's unfortunately missing right now? Do you have any,
Yeah, that's a very interesting question. I used to plan to put something on this slide, but it's difficult to say. So you can find out there are a lot of things I built myself. So for example, the service using shared memory. On Kubernetes, all the services are basically assumed to be exposing some APIs through network. While shared memory across pods, I built a few mechanisms myself. Probably this can be something the Kubernetes provide. A second thing about supporting this kind of computer stick, while Kubernetes has a device plugin model, I find it's difficult to use that model to support these kind of devices because of its own initialized nature. And third thing is about the load balancer. Now I'm duplicating this input image across all nodes, while the Kubernetes service only load balancing into one pod to receive the input. So if Kubernetes have another kind of load balancer, maybe helps this scenario, but I don't think there's a common scenario, but anyway, I don't know. So also the scheduler, I'm not sure if it's worth to support the core level scheduling. Maybe it's not the task for the scheduler, but I don't know. Thank you.
I have a quick question. You mentioned the slide about Kubernetes on ARM. My question is, what was the most challenging task working with Kubernetes on ARM?
Well, that's an interesting question. At the beginning, Kubernetes supporting on ARM is very limited, so you will hit a lot of problems compared to the x86 platform. While today it's quite a lot mature, and you can find most of commonly used image already built supporting the ARM, so you can pull down ARM-based images. But you are still missing a lot of useful images which only support the Intel platform. And the other thing about the cores, so the Big.little architecture is very special, and I don't think that is well supported in Kubernetes. So I think we have reached the time limit. I will be hanging out for a while, especially around the booth area. So I'd like to have a further discussion if anyone has interest. And I also want to learn something from you if you have some expertise on computer vision or anything. Thank you. Thank you for your attendance.